This is the fifth video of the section, Sampling from a Normal Distribution. In the previous video, we learned to generate Poisson random variates. In this video, we'll demonstrate how R generates samples from a normal distribution. From observing real-world data, we may determine that most data follows a normal distribution. That is to say, when we use a density curve, or histogram, to plot the data, we should see it as a bell-shaped. As this kind of distribution is so commonly seen in nature or social science, scientists often use a normal distribution to represent real-value random variables from an unknown distribution. A normal distribution is known as Gaussian distribution, which is defined by a variate x with the means as mu and variance as sigma square. As the distribution curve is shaped like a bell, some refer to normal distribution as a bell curve. The probability density function can be defined as the following formula. You need to prepare your environment with R installed. First, you can use the R norm function to generate 30 and 1000 samples from a normal distribution. We have 30 samples for data 1 and 1000 for data 2, as seen here. We can then use the hist function to plot the histogram of data 1 and data 2. This is the output of data 1. Now let's see the output for data 2. You can see both the histograms clearly. Also, you can extract the density property from the sampled data and add a density curve onto the histogram with a lines function. This is the code. You can see the output here with x and y values. These are the values for minimum, mean, and max. Then we use lines function to plot the curve. You can see the density curve over histogram. On the other hand, you can compare the distribution under different standard deviations in a density plot and histogram. First, we'll plot using the plot and lines function. You can see the red graph is steeper. Then we use hist for plotting histogram of data 3. And here is the histogram. Now the histogram for data 4. You can see the changes in the histogram. Also, you can compare the distribution under different means with a density plot and histogram. We'll use data 5 with R norm and plot it. When we plot it under different mean using the line function, we get this output. Now we plot the histogram for data 5. You can see this here. When we plot histogram for data 6, the output is changed as is visible here. On the other hand, if you would like to plot a perfect normal curve, you can use the curve function to connect the height of probability distribution from -3 to 3. Plot the function. I've plotted the graph here. We can also shade the area under a density curve. The code is as follows. We give the polygon function x and y values with the color blue. Here we'll shade the area between -1 to 1. To get the height of probability distribution at 0, one can use the d-norm function. Here's the height. Moreover, to compute the area under the curve between x from -1 to 1, you can use the cumulative distribution function, the p-norm function. You can see the area here is 0.6826895. To plot the graph of p-norm, a curve function can be used. This is the curve function. When we execute this code, we see our curve. Moreover, to calculate the point that the distribution accumulates a particular cumulative density, one can use the quantile function qnorm to inverse p-norm. In this sense, we can use qnorm to retrieve the approximate value of 97.5 and 2.5 percentile points of a normal distribution. Let's use qnorm function. And here is the output. As per the red shaded area, we discover that 95%, from 0.025 to 0.975 of the area under a normal curve lies within approximately 1.96 standard deviations. In this video, we learned to work with normal distributions and collecting samples from them. In the next video, we'll sample from chi-squared distribution.